Before we talk about the energy of springs, I'm going to describe some basic properties of springs. So first, when a spring isn't moving, when it isn't compressed or stretched out, it's at rest, it's in equilibrium. And in equilibrium, we say the spring has no potential energy. So we define a point, which we call x naught often. That's the equilibrium point, and at that point, there's no stored energy because it's not compressed. When we compress it or stretch it, we're going to have more potential energy, and if it's at its most compressed or most stretched point, it'll have the greatest potential energy. And so here's our equilibrium point, and we can have more stored energy as we stretch it, and when we reach its maximum, which is its amplitude, it's all potential energy. And when it reaches its minimum or its most compressed, it's all potential energy. So you can think of the spring at this end as potential, at this end as potential, and once you let go of the spring from any of the stretched points, it'll be kinetic in between, and at the very center, at this point here, it'll be all kinetic energy. We're going to talk more about these details of harmonic motion later, but I want you to just think about the potential energy of a spring happens any time when it's not at its equilibrium point, and it's greatest when it's at its most compressed or most stretched point. When you release the spring, the energy changes from potential spring energy to kinetic energy. So the most kinetic energy you would get would be right in the middle. That's when there's no potential energy. Because springs are conservative forces, we're going to say that the spring energy will all get transferred to kinetic energy. So there's another property of springs that we use when we do calculations, and it's called the spring constant. Each spring has its own spring constant, and we use the variable little k to be the spring constant. So if we take a spring, it's in equilibrium, and I compress it a distance x with force F, we're going to give it potential energy. As the x increases, so does the force required to compress it. And that force depends on the distance it changes and on the spring constant. The force it takes to compress the spring is equal to, and this equation is on your equation sheet, the force of, the little s means spring, the force to compress a spring equals k times the x. You'll notice that it is a absolute value of x, and that's because it's the same force if you're pulling out the spring, then your x would be negative, but that negative, we're just going to look at the magnitude of the value, not the negative part of it. So the force is equal to this constant, which is different for each spring, but it is a constant for a spring, times the displacement, or the amount that it was compressed. K is a spring constant. Its units, you can see this is going to be in newtons, and x is going to be in meters, so the units for K are newtons per meter. X is the amount the spring is compressed or stretched. We also can use that K to look at the potential energy of a spring. And the potential energy of a spring looks similar to kinetic energy, but not exactly. We call that U sub S. U is for potential energy, S is for potential spring energy, and it's equal to 1/2 times the K constant of the spring times the displacement x squared. So if the x is at 0, right here, in equilibrium, our potential energy is going to be 0 because x is 0. And if I increase x, I will increase the potential energy of the spring. So let's do a simple problem. We have a spring, and sometimes you'll be given the spring constant, sometimes you'll be asked to find it. We have a spring with a spring constant of 300 newtons per meter. It's stretched from equilibrium by 0.5 meters. What is the energy stored in the spring? So we're just going to plug those numbers into the equation for spring constant, or for spring potential energy, and we get the potential energy, spring potential energy is 37.5 joules. And the units for energy for a spring are the same as the units we used for gravitational potential energy and for work. It's going to be joules. Let's look at something a little bit different. We're going to remember that spring is a conservative force, so spring energy will be conserved. What's going to happen to the spring energy as the position of this object changes, as the spring is compressed more and more? It starts here, at its most stretched point, it has 0 kinetic energy, but it has stored energy of 4 joules. So we're going to compress the spring a little bit. It's not all the way to equilibrium, it's just partly. So it's kinetic, now it's been basically we had it here and we let go. Now it's moving, it has a kinetic energy of 2.6 joules, so what's the potential energy? You get that answer by noting that energy is conserved. It started at 4 joules, and we take 4 minus 2.6 to get its potential energy. So it should be 1.4 joules. This next point is right in the middle. It's at equilibrium, and you can tell that because its potential energy is 0. It must be all kinetic energy, so its kinetic energy has to be 4 joules. Then, as it compresses more, it has less potential energy. It has more potential energy, and it's also going to have less kinetic energy. Then it reaches its maximum compression, which will be 0 joules, and here its potential energy will be all potential energy, so it'll be 4. So the numbers to fill out for this will look like this.